That was an actual jump scare right there.
Blood is pumping. There we go. Anyway, hello everyone. Thanks for coming around. So yeah, this is the academic talk night. Was the first one of the term. Really exciting stuff. I'm the new, well, kind of new academic director. Anyway, we've got 3 speakers tonight talking about, a range of things, particle physics and all. Now, how it's just generally structured is we've got the speakers speaking for around 25-ish minutes. Then we'll have a 5-minute Q&A panel afterwards. And then between that, we'll have an intermission. Now, I'll check when we have this. So in the intermissions, I'm going to bring out some lovely catered food, a full fruit platter with pies, and you can take what you want. Now, one more thing is I've forgotten to set up a QR code for attendance. On the way out, if you guys, I'm going to set up a piece of paper just at the door. Just put down your name, just because then I can see who's been here.
And ZID.
And ZID. Yeah. Thank you. Other than that, I'm going to stop yapping because I've got nothing else good to say. Anyway, there we go.
Thank you, Josh.
Okay, thanks. Thanks a lot for organizing it. It's actually great. It's great to have it. Great to have that initiative. I will tell a little bit about what we are doing. So I'm Michael Schmidt. I'm one of the academics here. I'm working on particle physics, on theory. And so I'm not the only one working on theoretical particle physics. There's also Deepan Singh Gupta, there's Yvonne Wong, and then Jan Hamann. So it's going more and more in the cosmology direction. But yeah, I think that's the people who typically have the seminars together and we have this joint journal club. Okay, so feel free to interrupt me at any point. If I'm saying things which you haven't seen, tell me, and there's a whiteboard, I can explain it. And so yeah, we just want to give you a flavor of it. So what we are looking at, it's basically looking at new physics, or anything which is beyond what we currently know, which is the so-called standard model. So let me briefly revise what we know. So in current status, so you probably have seen a picture similar to that. So that's the standard model particle content. So there we have the, on the top are the quarks, up, down. We have a laser pointer or pointer device. It doesn't matter. Don't worry, I have here my mouse. So we have here on the top are the quarks. So up, down, charm, strange, top and bottom. Below here there are leptons, electron, neutrino, muon, neutrino, tau, and tau neutrino. And here we have the force carriers, gluon, so for strong interactions, photon for electromagnetic interactions, and then weak interactions, W and Z, and the Higgs boson up here. And so one peculiar thing of the standard model is we have basically 3 copies of all the particles which we have. They're sometimes called generations, sometimes called flavors. So basically up, down, electron neutrino is the first generation. And basically all what we know, so kind of nuclei and electrons are made up of that first generation. Right? So a proton consists of 2 up quarks and 1 down quark, and a neutron of 2 down quarks and 1 up quark. So this is the particle content which we have in the standard model. And so one thing is that generations get heavier and heavier. So if you go to second and third, that's basically it gets heavier. So, but there are also some unexplained observations in the standard model. So, for example, what you can see here, the neutrinos, I didn't write a mass. I think it's too small for you to see. So there is no label here. So while here we have some labels for the masses of the particles. We don't know what dark matter is. There are many different possibilities what it could be. We don't know why we have more matter than antimatter in the universe, and the standard model cannot explain it. And there are some other anomalies which are around, which I'm not going into. So basically those 3 are the main evidences for that there has to be some physics beyond the standard model. There are also some theoretical issues, so theoretical concerns. So you don't see gravity in that picture. And that is because we don't know yet how to properly incorporate gravity in the standard model or into the quantum field theory. Certain things we know, for example, if in the weak gravity limit, you can quantize gravity. And that works all well, but it's more difficult if it's becoming strongly interacting. Gravity becomes strongly interacting. Another question which we don't know is why are there those 3 generations? And why is there that hierarchy between the fermion masses, which we have there? So theorists are thinking about it and are looking and finding it out or coming up with ideas, but there is no clear reason for it. Maybe one reason could be is the matter-antimatter asymmetry, because in order to generate a matter-antimatter asymmetry, I need CP violation. So that's so parity is not conserved in the standard model. So basically parity is mirroring at the origin, and also charge parity is not conserved. When I at the same time mirror the universe at the origin and then change particles to antiparticles and vice versa. That's charge parity conservation. That's not conserved in the standard model, and that is necessary to generate a matter-antimatter asymmetry. And that's only there if you have 3 generations. Yeah. So if one looks at it a little bit more from a theoretical perspective, we have to write down a Lagrangian, or basically in particle physics, basically all theories are described by a Lagrangian. So who had classical mechanics already? So a few had it. So others not. So basically Lagrangian, so for those who didn't have classical mechanics yet, is basically just kinetic energy minus potential energy. And it works exactly in the same way for fields. And don't worry about the details. There's only one point I want to make. So I basically, we postulate the symmetries which are there. So basically just some underlying symmetry principles. And we postulate which fields and which particles are there. So here those L, Q, E bar, B bar, U bar, H. So E bar would be a charged lepton. L also corresponds to the leptons, and Q, D bar, and U bar describe the quarks, and H is the Higgs. And as soon as we have the symmetries and the particles, we can write down the Lagrangian. Then we basically write down all possible terms I can write down in a Lagrangian. And so here you see it schematically, sorry, that EH is apparently doubled. Should be only one part. So the part which I want to look at is this one here below. That's for the leptons, for the fermions, I should say. And so you will notice something. So if I multiply the lepton doublet here with a factor of e to the I alpha L, and I multiply E bar with e to the minus I alpha L, then this one remains invariant, that whole Lagrangian. So if I basically just start with those symmetries, SU3 cross SU2 cross U1, which describe then also the forces, in the field content, I get some accidental symmetries, which the Lagrangian respects. And so for those who had classical mechanics, they know always if there is a symmetry of the action or of the Lagrangian, then there is a conserved quantity. And so the conserved quantity in that case is lepton number. So the total number of leptons, so basically adding up electrons, muons, taus, and neutrinos, and subtracting off the number of anti-electron, so positron, anti-muon, anti-tau, and anti-neutrinos is conserved. It always remains the same. And similarly for baryon number. So both of that has direct implications. So for example, baryon number, if the number of baryons is conserved, then I cannot have a process which basically destroys a baryon directly, right? So what is now the lightest baryon which we have in the universe? Does anyone know what is the lightest baryon? What is a baryon?
Look at me, Marcus.
Huh? James knows, but so baryon is, for example, proton and neutron, and the proton is lighter than the neutron. The proton is the lightest baryon which we have, and so what that means is if baryon number is conserved, which it is in the standard model, then the proton is stable because it cannot decay. There is no lighter baryon it can decay into. So for leptons it's less important because neutrinos are very light, so you can always decay into neutrinos. But for the proton, it's basically the proton is stable. So that's one prediction of the standard model. So if you want to go beyond the standard model, I said if we want to go beyond the standard model, there we can use a tool which is called effective field theory. So I will give you a heuristic explanation or motivation why we want to use something like that. So what we generically find is that the description of physics at low energies or large distances does not depend on the dynamics at high energies. So in one example, let me give you an example which is very clear. So when you calculate the hydrogen, when you look at the hydrogen atom and calculate the energy levels, you only need to know the charges of the electron and the nucleus, and you need to know the masses. Actually, it's enough to know the electron mass because that's lighter. And you don't have to worry about that the proton is actually not an elementary particle and made up of quarks. It basically doesn't matter at all. So that's basically, so we can work with an effective description where we work with the proton directly instead of the quarks, which describe the underlying physics. And so technically we work with an effective theory there, where we basically work with protons and neutrons instead of quarks, which are the more fundamental objects. And so the same thing one can do in particle physics. So for example, if you, let's stay with the neutron. So you all have heard about beta decay. So beta decay, there a neutron decays into a proton, into an electron and a neutrino. That's basically what I have here. And so in the standard model, that process is described by exchanging a W boson, so which is the force carrier, one of the force carriers of weak interactions. But if I'm looking at a neutron decay, so the relevant energy scale is basically the mass of the neutron, which is there. And so the mass of the neutron is in natural units, 1 giga-electron volt. And in comparison to the mass of the W boson, the mass of the W boson is about 80 giga-electron volt. So there's a factor 80 in between. So what I can do is I can do an expansion in the neutron mass squared over the W boson mass squared. And that's basically exactly what we do here in that effective field theory, and describe it in terms of an effective vertex where I don't see the W boson. Basically, I remove the W boson from the theory and I replace it with an interaction which describes the same. Where basically a neutron goes to a proton, electron and a neutrino. And so the point is I don't have enough energy to resolve those small distances. So the W boson here, that lives only for a very short period of time, and I don't have enough energy to resolve that. And effectively what this is a Taylor expansion, what you're doing there. And that's an effective field theory. So an effective field theory is if I replace fundamental particles by just those contact or point-like interactions, where I don't resolve what's actually going on in here. Okay. So that was very successful. So for Fermi theory was one of the hints that there should be something beyond that. So one can actually, if one goes a little bit deeper into that, Fermi theory, which is basically describing neutron decay by this operator, cannot be a fundamental theory. There are some problems. There is a cutoff. And it can only be true, sorry, I forgot to write that down. So it can only be true that it can only be valid up to roughly 200 giga-electron volt. And there, if I go to higher and higher energies, so before 200 giga-electron volt, I should have find something else, something which is underlying that interaction. So now, of course, here we know it already because we know the W boson, we know the standard model, it's measured very well. So we can do the same thing now if we want to look for new physics beyond the standard model. And so we basically, what we do is we treat the standard model as an effective field theory. We introduce additional interactions in the standard model where you have here some operators just schematically written with some coefficients in front. And so those operators, they parameterize anything which is beyond. They parameterize what should come beyond. And so what's important is that's a series and that there is something what is called power counting. So meaning there is basically the operator of dimension 5, the lowest dimensional operator, is more important than the one at dimension 6, than the one at dimension 7, and so on. So if I go into Taylor expansion, if I truncate it at the first non-trivial order, would be kind of dimension 5 here, and so on. I can go higher and higher in that order. And so people classified it and looked at this. And so at dimension 5, there's only one operator, which is there. That is called the Weinberg operator, which has been found in the 70s. And so that operator, that violates lepton number. So this operator here, if I multiply my L, my lepton doublet, with a phase factor, and then I see that this is not the same. It doesn't remain the same. So that phase factor doesn't cancel out. So what that means, it violates lepton number by 2 units, and it will lead to neutrino masses. So lepton number, which we've seen was an accidental symmetry, is actually broken if we go to that effective field theory picture. So we should expect lepton number to be broken. The same thing if I go to dimension 6, there are 42 operators. I'm not going through it. So then there are specifically some operators of this form which have 3 quarks. And those operators, they violate baryon number. So we saw that baryon number was a conserved quantity in the standard model, but if we go to standard model effective theory, we see that baryon number should be violated, or there should be the proton should decay at some point. And that's also a prediction which one finds in underlying UV models like grand unified theories. You see that the proton will decay. That's one of the predictions of grand unified theories. And the scale, so if one looks at the experiments which search for proton decay, which technically are just big tanks of water, and you look in and just count whether a proton decays in there, put limits on that scale, the scale associated with that operator. So this scale here, that scale lambda of 10 to the 15 giga-electron volt. Just for comparison, the proton has 1 giga-electron volt. Right? So mass of the proton is 1 giga-electron volt. Largest collider energy at LHC is 14 tera-electron volt, so 10 to the 4 giga-electron volt. So this one is 11 orders of magnitude higher. That's the strongest limit. That's probably probing the highest energy scales. So what I wanted to briefly talk about, I'm doing with time.
Yeah, you're fine.
Fine, okay.
You're going well.
It depends how many slides. You don't know how many slides I have.
Oh, there you go.
No. I just want to give a little bit of flavor what we have been doing or what we are working on. And so one is kind of to use those effective field theory techniques to look at proton decay. So from a bottom-up perspective. And so this one is, I should have put a reference there, but that's the, so here you see the current limits. So the super Kamiokande experiment, which is in Japan, puts the most stringent limit on proton decay, here on a specific decay channel, proton going to positron plus pi 0. And you see here in red, this one is a proposed experiment at hyperkamiokande in Japan that will improve it by 1 order of magnitude. And that probes in terms of the lifetime of the proton. So that puts a lower limit on the lifetime of 10 to the, so currently of 10 to the 34 years. That's much, yes.
So just with the, if you're decaying from a proton to like an lepton, and is that a meson?
Ion? Yes, that's a meson.
Is that kind of like, because I know baryon number, like you're saying that it has to be broken, but is that, I don't know, in my mind, I feel like that's almost like making things more complicated. It's like now you get 2 particles, you got a lepton there, you got a pion there.
Yeah.
Like, I don't know, it feels like it should be, that violates something. I don't know how to put it. Like you said that the proton kind of, baryon number is kind of meant to be conserved, but like how are you then producing a meson and a lepton in a lot of these cases?
Okay, so there is new physics, so like grand unified theories, which predict the proton to decay. So where the baryon number is actually not conserved. And so that's a very sensitive, so proton decay is a very sensitive probe for that. If we observe proton decay, if we don't observe proton decay, we can put a limit on where that grand unified theory could be. And if we observe it, that could be one hint that there is a grand unified theory. Or some other theory which violates proton decay. So that's just one example. It's probably most known. Yeah. So we know, and from an effective field theory perspective, the point is basically that there are those operators. You would naively expect them to be there because we didn't impose that symmetry from the start. That's the point. So the barrier number conservation is not an imposed symmetry. It's just an accidental symmetry, which.
So you wouldn't say that that value is a what's the word I'm looking for? Conserved value in the Lagrangian at all?
It is conserved if you only take the part of the standard model.
Right. Okay.
But if we look beyond, it's not clear whether it's conserved.
Cool.
And why it's interesting, it's interesting because it's a very sensitive probe for those new physics scenarios where barrier number is violated.
Yeah.
Yes. Any other questions? No? Good. Then.
Well, actually, yes.
Yes.
maybe.
That's good.
I don't know if it's silly or not, but how did they find, like, is there a relationship between how many operators there are in each dimension?
There is a relationship.
Because there's a bunch of symmetries always, so like.
Yes. So I haven't worked on that myself. So I should say. So you use. There's first of all the symmetries. So the question is, how many invariants can you write down? So this operator here has to be invariant under all of those symmetries, SU3 cross SU2 cross U1, and then Lorentz symmetry, and so on. And you can then basically just start constructing all of them because you have the basic building blocks, you have the fields, Q, L, E bar, U bar, and so on. And there's a systematic way how one can construct it. That's called invariant theory, which has been mostly developed in the 1900s, 19th century. So there is a tool which is called Hilbert series. And that Hilbert series tells you how many invariants are there at every order. So the authors who basically looked into that was Hitoshi Murayama and his collaborators in Berkeley. They used some other tools as well to basically remove operators which are related to each other. So there are many relations between them, such that the number of invariants is smaller than what you naively expect.
At that point, does that just become like a maths problem?
It's a math problem.
Yeah,
It's a math problem in the end. But the Hilbert series techniques, they are now have been used a lot in the last 10 years. Or probably 15 now. 15 years. So that one for the standard model EFT has been done probably in 2015-ish, where they classified it, so in the early 80s, they already did up to dimension 6, because these are the most relevant ones. And now in probably 2015-ish, they came up with a systematic way how to go to an arbitrary order without basically sitting down with pen and paper to classify it. Any other questions? Yeah. But if not, then let me comment a little bit on that. So what we looked at proton decay or barrier number violating nucleon decay, to be more precise, because there's also neutron decay, which from a bottom-up perspective, and so I'm just having here a cartoon. The details are not too important, but what one can do is one uses effective field theory. So there is 3 levels of effective field theory which one has to use to calculate proton decay. So at a very high scale, you would have here the theorist who comes up with some crazy theory, with some grand unified theory, or some supersymmetric theory which predicts proton decay. Then from that theory, one can calculate what are the induced operators, and the ones which are relevant are at dimension 6 and dimension 7, which violate barrier number. These will give the dominant effects. And then at the scale of the W boson, one has to remove the heavy degrees in the standard model, meaning the W set top Higgs. It goes to something which is called low energy effective theory. But then later, at the scale of roughly 1 GeV, you have the correct description is actually not in terms of quarks, but in terms of hadrons. So you have to switch again your effective theory, and you go to something which is called baryon chiral perturbation theory, where you basically work with mesons and baryons instead of quarks. So it's a series of effective field theories which one can use. There's an alternative down here. one can also just put it on a computer and do a lattice simulation. So if one does that, one can then basically derive limits on basically assuming that there is a certain operator generated. You can derive limits, and so that's what we did. So these are dimension 6 operators, and so the other thing which I wanted to mention is in a quantum field theory, you have that parameters in the Lagrangian will depend on are not constant. So one thing, one argument for what some of you may have seen is basically that the gauge couplings, the couplings of the kind of the strengths of the force carriers change with energy scale, and they meet at a high energy scale. That's the motivation for grand unified theory, and the same happens for all other parameters. Yes.
That just to check my understanding, that's like the whole at the start of the universe when you have those high energies, those decoupling periods of time. That's like the thing which you're referring to, right? Like with the force carrying.
Yes. So at high, so that would be at high temperature.
High temperature.
But also, if you go to high energy, you would see that the forces become different. So, for example, the strong force gets weaker and weaker if you go to higher and higher energies, while electromagnetism, the weak force, gets stronger. And so one should include those effects, and that's basically what you see here, basically in light blue, including those quantum corrections. So that's basically quantum effects which modify those naive predictions, and they will give you a factor of, give you 50% or so correction. And you can ask me later why it's larger for dimension 6 than for dimension 7, but that's a detail. So what you can do now, basically we provided a tool for other theorists to take that, and basically when they have a theory to basically just calculate those operators which are generated, and then we basically have the results to immediately calculate proton decay, to make the prediction for proton decay. So the other thing is, what one may wonder is there are different contributions to proton decay. Can there be cancellations that I miss it, right? So can there be different contributions which just align in such a way that proton doesn't decay? And the answer is no. So we have here, for one example, where one compares two operators which are there, and you see that depending on the decay modes, so that's a proton to pi 0 e plus, that's basically here's a cancellation, and I basically don't get any constraint on it. But here for proton to eta 0, so a different meson, e plus has a cancellation there, but if I take it together, it's impossible to avoid those constraints which are there. So we should find proton decay if it's there. That's basically the message. And one can, the same thing, I think I should finish, can look at if one introduces phases to that, it makes it slightly more complicated. So I think the takeaway messages which I wanted to give is, so effective field theories are a very powerful tool to describe physics at low energies. And so they are those accidental symmetries which are there in the standard model. So those baryon and lepton numbers, one should expect those to be broken. And those, there are upcoming experiments like Hyper-K and Dune, which will probe basically those proton decay and will probe the highest energies. And if you're interested in research like that, basically looking at using effective field theory, also applied to other contexts. So that's kind of one direction where we apply it to, then talk to me. I'm happy to explain more. So most of it, the research what we do requires quantum field theory, which is of course only an honors level course. But one can do projects with neutrino oscillations, one can describe with quantum mechanics. Just there one doesn't need full quantum field theory picture. Thanks a lot. So I'm happy to answer any questions you may have.
Yeah, actually, I do have one just to do with the different models that you had at the different energy scales.
Yeah.
So with the lower energy scales, like the hadron level, is that just like a statistical estimation for what's happening at the quark level, or is it like a completely different model? Is it like kind of like you're dealing with a micro and macro system, you're just estimating the micro with stats?
It's a different model. So what you do is basically we know the symmetries in that low energy effective theory, and we can write down and we use symmetry arguments to connect the two theories to each other. So what's happening there? I'm not sure in how much detail I should go. So there is basically SU3 cross SU3 symmetry in the low energy effective theory, because if one neglects quark masses, you can basically not distinguish up, down, and strange quark from each other. And that's that symmetry. But if you then go down to lower energies, that symmetry is broken down to a SU3. And so from there, you can argue that they are Goldstone bosons. So every time you break a symmetry, a global symmetry, you predict massless particles. And so those massless particles are the pions in the kaon. And so I can write down a theory for those pions and kaons. And that's chiral perturbation theory. And then I basically use symmetry to match the two theories together. I can predict it up to a finite number of, or a discrete number of constants, which I have to determine from experiment or from lattice simulation. Yeah, but it's technically a different quantum field theory which you connect.
No one else has any questions? Thank you.
Actually, maybe.
Yeah.
What other contexts do you apply effective field theory to in your work?
In my work, so I do lots of flavor physics. So that's B meson decays. James will be talking about neutrinos, right?
I was going to talk about
the other one, that's the symmetries. Sorry, so my bad. So James is applying it to neutrino mass models, where we also use that effective field theory context. So effective field theories help to make actually also precise predictions. There is a way how you can, the calculations in the effective field theory are simpler, and you can include more quantum effects. That's currently I use it actually for most of my work. That as techniques, I have to say, yeah. So flavor physics of neutrinos. Here, I know people also use it for dark matter physics, because you have, let's say, you have a theory which makes prediction at a high energy scale. You have to connect it to what's happening there with dark matter. So what you typically use there is you go to a non-relativistic effective theory, because let's say the dark matter particle is very slow, it's cold, and it scatters off some proton. So you can work with a non-relativistic theory, which is also then an effective field theory. It goes under the name of heavy particle effective theory. So it's a concept which you can use in many places. And I'm sure in astronomy you have similar concepts where you can separate scales from each other, because you probably don't have to know about galaxies when you talk about stars. Yeah.
if you had to make a prediction on when we're going to figure out what dark matter is from a theoretical prediction, what's your number?
Oh,
5, 10, 15?
And what's your bet? What are you putting on it?
Yeah.
I bet it's. I don't know when I can attach a number to it, right? because we don't have any clue actually what it is. To be honest, right? It can be as light as 10 to the minus 21 electron volts, and there are constraints from astrophysics on, just from halos, and it can be primordial black holes and many solar masses heavy. So we don't actually know what it is.
I mean, it's an experimental problem, right? Like
Exactly.
Yeah, put the blame on us again.
Okay, so there is. I think experiment did an amazing job, right? If one looks at weakly, so those WIMP searches, they are basically getting to the limit of what they can do. They improved it over orders of magnitude down to that. It's amazing. And now, at the moment, axion experiments are pushing very much because people are interested in it and building experiments and come up with new ideas to test the available parameter space. And then, of course, astrophysics gives also many constraints on. We learn more about rotation curves and how it actually can cluster. Unfortunately, I don't know. I think it's really, I could bet, I could gamble on it. Yeah.
Within our lifetime?
I hope so. I hope so. I think that's one of the big things to find out what's happening with dark matter. We had today a talk in our seminar about condensed matter dark matter, where they basically looked at it could be a superfluid, or so you can have some dark stars with some strange matter, some Bose-Einstein condensate, or so it could have different phases. Yeah, so people are thinking about many possibilities. In the end, only one will be realized. Of course.
Yeah, I think that'll probably be a good point to wrap up. Thank you for speaking, of course. And what we're going to do is
Go for
All right, hello everyone. I am James. I am a PhD student of Michael's. He has not seen this talk, so hopefully he doesn't stand up in protest. Very nice man, I'm sure he won't. Okay, so I have called it Objective Beauty, only in part because I'm the one presenting it. But in the other part, that I think there's a sort of the first half of it is a talk in sort of general terms about building models. And then the second half will be more precisely, not that I'm building models, but what I'm doing. Okay. So I hope you've all appreciated this meme.
very well.
It will be the theme for the first half of. Okay. So what is a model? Well, so Michael pointed out that we had the standard model. He was talking about the Lagrangian. And to a particle physicist, a model means a Lagrangian. Okay, here are some various Lagrangians. It's rather information dense. The idea is that you go, ooh, it's a Lagrangian. How do we test a model? So we could take some Lagrangian. This is just a generic scalar field. It's called a phi cubed or phi3 theory because there's a term that has phi cubed in it. The Lagrangian is made up of, as Michael said, it's basically a statement about the energy. But you can surprisingly accurately interpret this as some interaction, as in there are 3 phi fields, so you have some vertex with 3 phi fields, and some parameter lambda that's the strength of this interaction. So how would you test the model? Well, you would build a collider and you would go and smash 2 phi particles together, and you would detect a phi particle, and you would calculate the strength at which that happened. So basically you just fit these parameters into your model. All right, so far so good. Of course, sometimes, like the neutrino masses, experimentalists go and measure something, and we don't have anything in our theory to account for it, and that's a pain. But we can always add stuff at higher energies. It's a little, yes.
I think the title is misleading. You're saying when an experiment fails us. You said you didn't have any theory. I think you're failing them.
Yeah, I thought about this title as I wrote it, and I thought, no, I'm gonna leave it exactly as it is.
It's a statement.
It is a statement, but this is a good point, and we should remember that physics is an experimental science, and at the end of the day, it is on us to explain the experiment and not the other way. Yes, this little quote I have is what it feels like sometimes. You know, if the latest experiment was at 13 teraelectron volts, well then I can do whatever I want at 20 teraelectron volts. You can't stop me. It's basically the life of the theorist. The point is just to say that there is such a huge amount of freedom we have in high energy model building. And for any, this is a very general statement true in science, right? For any set of observations, I can come up with a hypothesis that explains them in retrospect. The question is, can you keep doing that? And yes, in a sense, like it's totally valid in the scientific method, right? The scientific method doesn't care about where a hypothesis comes from. All it cares about is, does it give you correct predictions? And if you write down crazy, complicated, wacko theories that give you the right predictions, then so be it. As long as they're falsifiable, which most theorists have gotten pretty good at making sure that their theories are falsifiable. However, that's usually only falsifiable in theory, And in practice, you need, a couple of $100 billion to build a big enough collider. So that's okay, but the big problem is that that's inefficient. Kind of the point of what I said before, we have thousands of, probably more than thousands of models for what dark matter could be. But none of them is particularly useful if they're all far beyond what we can measure to differentiate. Okay, so how can we be more efficient? Well, the theme of this talk is that we can use beauty to guide us. This is the famous golden ratio. I think the first and third picture here are quite good examples of fitting. The middle one looks like someone's just thrown it on top of a rose and said, ooh, it fits. But I don't know whether that's true. But I thought I included it because I thought this is a good point to make, that we should be guided by beauty, and that it often does let us come up with good, accurate theories. But that's not always the case. Sometimes our theory is the rose, or perhaps our theory is the golden ratio put on a rose experiment. So we should always make sure that it's falsifiable and that we listen to it being falsifiable. But the point is, beauty can guide us be more efficient. And so how can we quantify what it means to be beautiful? And I've kept it rather straightforward, that a beautiful theory is one that requires less inputs and results in more predictions. Which then modifies our mean to vibes, but quantified. Okay, in practice, what am I talking about? So as we saw before, the standard model has 3 flavors of leptons: the electron, the muon, and the tau. And we have many ideas for new physics that solve all sorts of problems, some of which Michael mentioned. And a lot of those ideas introduce processes into the standard model that can violate this flavor, or a process that can change the flavor of a lepton. Or perhaps more accurately, remove a lepton of one flavor and create a lepton of another flavor. Yes, so we could just write down a theory with all the interactions that we observe, and it would be a correct theory in the sense of as far as we have measured so far. But a much more beautiful theory would be one where we had less parameters than everything we've observed. And so we want some dynamical explanation of this structure, which just means we want to assert one or a few number of things, and then that necessarily means that we get all the structure that we've observed. So what we do is we can introduce a symmetry into the model between these lepton flavors. Okay, so the maths of symmetries is groups. So in particular, sort of symmetries I'm looking at deal with these Z groups, which is just integers mod n. So some examples, if we assign the charges, if we are in this Z4, so we're integers mod 4, and we assign the charges as they're shown there, then any process that involves an electron, a muon, and 2 anti-taus has 1 plus 3 is 4, 4 mod 4 is 0, that conserves charge, that's in. If you have a process that's just got an electron and an anti-muon, that's 1 and minus 3, that's minus 2. That doesn't conserve charge, that's out. Okay, so when I say we can impose a symmetry, this is what I'm saying. So then we can look at different symmetries and different processes, and we can count all the possible ways. So this has basically been what my desk has looked like for the past few weeks. We can condense all that table into something much nicer. This here is a picture, which after having made this picture, I realized that the circle thing is not necessary. I could have made exactly the same diagram just as a regular rectangle. But I've spent too much time on it by then, so it's a circle.
It looks great.
In retrospect, the benefit of a circle is that any particular segment is on average closer to any other particular segment when it's a circle. So it's easier to compare justified, which is exactly what I was thinking. Well, what it shows you is that for a given symmetry, right, so each ring is a different symmetry, a different group, I'm compatible with different processes, right, different combinations of electrons, muons, tau. And so you can quite easily, let's say you go into the lab and you measure a certain number of tau decays, say you measure this tau decaying to E mu mu, then you know, well, there are 3 possible symmetries I could be in. To distinguish between those 3, I should maybe measure something else. Perhaps I want to see if I can measure this have to be in a collider, but tau tau EE. And then I would know that I have to be in either this 411 or 211. So we can take this a step further, and using this effective field theory technique that Michael was mentioning before, we can say, without caring too much about what my new physics model is in detail, just the fact that I end up with these processes, that's the effective field theory part, we can just assume that the strength of them all is about order 1, and we'll just stick with order of magnitude estimates. We can calculate what we expect. These are branching ratios. This is the you sort of think of it as the rate that a tau would decay into that particular set of products. So we can calculate the relative likelihood of decaying into any of those particular products. And so what this means is that if we, not only can we say if we observe or don't observe different processes, we know what groups we're in, but if we know we're in a group, then we know where we should look for other processes based on the energy scale that we first measured. So the idea being that by specifying only the group, we then know the structure of processes that are allowed, and we actually, moreover, get the sort of order of magnitude scale of these processes. And so thus is the idea of beauty. So if we want to build these models as beautiful models, then we should at least attempt to find this dynamic explanation, which is to say we can enforce a single symmetry and get out a whole set of structure from it. We should stress that there's no reason that nature should be as beautiful as it is, other than it's worked for quite a lot of physics to assume that nature's beautiful. And then this is another nice meme, which again is getting at the idea of beauty, because if you can, much like the standard model, you just say standard model is SU3 cross SU2 cross U1, and it has this field content, and then that tells you all the structure. So physicists are very happy if nature follows groups. Yes, that was it. That went 26 minutes.
Can I ask about the arrangements with the circle diagram, the very lovely looking circle diagram? So when you're talking about like 2 to 1, 1, 2 to 1, 0, can you just explain that a little bit more in terms of how you gain those results? Like in terms of like what each of those means specifically?
So these label the charge assignment. So if we go back by charge assignment, I mean this. So let's imagine we're in Z2. Right, that's what 2 means. And then the 2 numbers I had on that circle diagram are the difference between each charges. So 3 charges, 2 differences. So if I was in 2, 1, 1, that means I've got Z2 with charges 0, 1, and 2, which in Z2 is also 0, so 0, 1, 2. That's because when we only care about conservation of charge, whether the charge is conserved or not. We don't care what the actual value of the charge is. So the only thing that matters is the difference between charges. So that's what that notation is. And then for a given group, you can just basically guess and check all the different charge combinations and see what operators are allowed and what are not. Of course, to do that systematically, I've done that in code. I haven't sat down and actually counted every single one myself.
So then the ones that are coloured in, then those like the possible arrangements or possible like charge differences that.
Correct. So in this group 201, I can have any operator that's got this dark.
Yep.
And similarly for.
Cool.
Makes sense.
It's just counting, basically.
Yeah, I could see that actually makes sense. That's crazy.
If you've done first year, as in like first year of schooling.
Yeah. I like that.
Can I just ask, on like a day-to-day, what kind of physics are you mostly doing? Like you just mentioned you count a lot, which is kind of like StatMech. No, it's kind of like StatMech because you can count in StatMech.
So with the
Like
abacus or
groups
the-
is kind of like abstract algebra, number theory kind of vibes. Like, what are we doing on a day-to-day?
So I have two projects. This is one of them. The other one was what I talked about last time, the Z model stuff. So that's calculating neutrinos, doing running. So that's all differential equations. So far, the quantum field theory has kind of just been set up the problem in this problem. And then, that project was differential equations. This project is groups. And when I say counting, I'm thinking about groups, right? Because to do it systematically, you're doing it. Yes. So it's a lot of both projects are using a fair bit of code, but not like simulation code, like numeric code.
Does that mean I should be paying attention in my numerical methods class for when I do this?
I'm not. So I did a numerical methods class in undergrad, and the lecturer, I think it was just genius advice. He said, don't try and learn the details of every method because you're never going to remember it and you won't need everyone anyway. Just know what different methods there are, and when you need one, you'll know what to do.
Yeah, okay.
Right? Which I find very useful when I'm doing the differential equation stuff. Because different differential equation systems have different properties that make different solvers more efficient.
Yeah.
And I don't remember in detail how all the solvers work, but I remember that there's different categories.
Yeah, I haven't even learned the different categories yet because I'm not paying attention to all. That's correct.
I think it's a good idea to pay the minimum amount of attention that you should. Cool.
Sweet. Well, we'll have a little.
Shall we continue?
Yes.
Yeah.
All right, last talk. There's one equation in there. No worries. It's not going to be as heavy as maybe some of as the other talks.
First year, first term. Don't know any of that stuff.
Exactly, that's what it's aimed at. So the title is, what do galaxies and shadow puppets have in common? It's a thing I love doing for my nephews and nieces where you're like in front of a lamp and you're like doing like, what animal do I do? I'll explain how this connects to galaxies and how you can use techniques like shadow puppets to actually understand how galaxies work. So that's the key thing of the talk. For those of you who don't know me, I'm Jesse. I've had an interest in astronomy since I was 16. I've had a passion for astronomy since my first year at university. My first lecture in special relativity was that turnover point for me where I was like, I don't want to do anything else. I have a fondness for observations, data reduction, analysis. In particular, observational astronomy is the thing that I love the most. But then when I'm trying to do research, I look at stellar populations and kinematics, so how stars move in galaxies. When I'm not working, you'll see me on the beach here at Coogee, playing beach volleyball. I love free diving, I love bouldering, and I've got a weird fondness for cutting down big trees. I don't know if that's a primal thing, but it's one of my things. So the work that I do is revolves around what we always in astronomy call the big questions. And so the light isn't great. Julian, could you do the medium light? Because it's some cool galaxy images. This was taken by...
Already on low, I think.
This is already on low.
Turn it up.
Oh, it's going to be super dark. No, I'll leave it as is. That's fine. What you can see here is the Milky Way, right? This is the Milky Way at Siding Spring Observatory. This is the Anglo-Australian Telescope taken by a PhD student called Delia. The Milky Way is a home galaxy. It's a galaxy that is very typical at first sight, has about 200 to 400 billion stars, forms about 1 to 2 stars per year, which doesn't seem like a lot, but if you multiply it by a billion years, you've got a billion stars. So it's actually quite considerable. The big questions that I'm trying to answer in my research is our Milky Way unique? Is it one of a kind? Or is it that really special one that can only be explained by a super special theory? Is the Milky Way formed through lots of mergers, or was it formed by just a giant cloud of gas that collapsed altogether? And then the thing that I'm particularly fond of is the Milky Way in its final stage, or will it actually evolve further? And so the thing in particular on that last point, we already know the Milky Way is going to change. Not soon, in about 4 billion years, but we're on a collision course with this little speck on the night sky that's called the Andromeda Galaxy. If you fast forward to 2 billion years, it's going to look really amazing on the night sky. The optimal time to live as an extragalactic astronomer is probably in 3.75 billion years, when that whole thing will fill the night sky.
That much.
So close. So close. So far away.
So jealous of what they're going to have.
The first real interaction that we're going to have, meaning that we'll feel each other's gravitational forces in a way that is really disruptive, is in about 3.85 billion years. And that merger, as we call it, is going to stir up all of the gas, is going to create lots of new stars. And then it's going to look messy for quite a while. You'll have your first passage, and so this is when Andromeda is flying through and away from us. But then around 5 to 7 billion years, it will settle into what we think is called a giant elliptical. Meaning when you have two galaxies, disk galaxies that are colliding, you create something that is much hotter, dynamically speaking. So meaning the orbits go from these perfect circles to like all of these chaotic orbits. This is what we think the final stage of galaxy evolution looks like. So in my PhD, it was all about finding galaxies like these in the early universe. The idea being that if you're looking for the final product in galaxy evolution further and further back in time, you might actually learn something about when those first galaxies formed, what that means for galaxy evolution. Now we know that, like at the start of my PhD, probably we thought these were formed maybe 10 billion years after the Big Bang, so we first needed to have a long period of normal galaxies forming. We're now finding these things 500, maybe 500 million years, maybe 1 billion years after the Big Bang. So galaxy evolution has made this huge transition of universe starts out as these little clumps and then disks, and then finally you have these big ellipticals to stuff happens really fast, really intense. But today's talk, as I said, we're going to talk about shadow puppets and how we can use that theory to understand how galaxies form. Some of you might have seen this diagram before. Astronomers love putting things in very simple bimodalities or tuning forks. And so this is Hubble's tuning fork. Hubble was one of the most famous astronomers who did the first distant measurements to nearby galaxies, discovered that the universe was expanding together with other people like Lemaitre. The key thing is, when he looked at galaxies, he saw basically 3 kind of categories. He saw these normal spiral galaxies. Then he saw spiral galaxies that have that giant bar in the middle, so he called these barred spiral galaxies. And then you have this other class of these ellipticals. On the left, he called them early types because they had spectra that were classified as early type spectra by other stellar spectroscopists. On this right side, you have things that are called late types. Has nothing to do with evolution. It's just the way we call things. Hubble thought already that stuff would go from here to here on the left. Turns out that's a pretty good guess. When you let a galaxy evolve over time, you either go from a disk galaxy to something that we call like a lenticular, which is like disky, but it doesn't have any spiral arms anymore. If you have lots of mergings or lots of collisions between galaxies, you tend to end up on that far left, these big ellipticals. The problem with this is, if we try to say something about the shape or how a galaxy might look like, here on the right, it's pretty obvious that when you look at galaxies and you see them at different inclinations, that you have a thin disk galaxy. So it's this beautiful disk, it's like a plate, and you know what inclination you're observing it at. Frisbee, if you see it flying in the air, you can pretty much guess whereabouts it is. But now think of a soccer ball, right? Or a volleyball, or even a rugby ball. If you rotate this, it still looks the same. If you spin it, it still looks the same. And so if I'm trying to figure out what the intrinsic shape of a galaxy is, it's going to be very hard to distinguish something that looks round because it's facing on, like it's facing you this way, versus something that's actually truly round. So that's the problem that we're facing. What we found though, and I'm already going to give the conclusion, is that it turns out that the shape of a galaxy is correlated to its age. Meaning that in the beginning, things look really flat, and as a galaxy ages, they become more and more puffed up. We did a press release on this, and some journalists went away and said, oh, galaxies are just like humans, you know, they suffer from middle age spread, they get thicker as they grow older. And I'm like, okay, maybe. So that was sort of the go-away title. Galaxies are similar to humans. They become a little more puffed up over time. So, the problem, right? We have a 2D night sky. Everything that we see is projected. Yeah, good spot. Everything is projected. And so if you had to convince yourself that some of these are true ellipticals and other ones are disk galaxies, you need some additional information. And so this is the problem that we're facing. How do you go from 2D back to 3D? And projection is really problematic in this sense, right? If I were to ask you guys, you're a bunch of aliens, you're observing this population on another planet, and all you see are these, other aliens walking around, and you had to guess how tall they were, that'd be super challenging, because we're just seeing the projection from above. In the same way, if I asked you who of these little people are wearing backpacks, or, have something else in front of them, it'd be really hard. So projection makes everything harder. And the same is true for galaxies. And this was the example that I already alluded to. If these are two galaxies, how can you tell that one would be an elliptical and how the other one would be a disk galaxy? Inclination ruins everything. So this one on the left could be both an elliptical or it could be face on spiral. This is the challenge that we face. And so this is where shadow puppets come in. Because if I show you these shadows, very quickly, like my nephews and nieces, you'll figure out like, wait, it's a projection. How do I do this? You use your fingers and you kind of figure it out, right? And so you're using additional information. You're using an extra dimension where you're like, I know it has to be constructed from fingers and I just have to find the right combination. And so the same is true for galaxies. You just have to figure out what is the distinguishing factor between something that's really round and something that's really thin. And it turns out it's rotation. Because if you think about classical mechanics, and if you think, in this case, about gravitational potential theory, one of the cool things that you learn is that in order to create something as thin as this, the orbits of these stars have to be going around like circles. If I want to create something that's dynamically stable, but that's really puffed up, the orbits have to be much more chaotic. And so if I measure what we say like rotational velocity and random motions in galaxies, I can make a prediction about the shape of a galaxy. And so this is what we do. We use the Doppler effect of light to measure galaxy rotation. And so here's, for example, a spectrum. We have all of these beautiful absorption lines. This is the sodium line. In rest frame, this is sitting around 580 nanometers. When the light moves away from you at high speeds, just like the normal Doppler effect for sound, the whole spectrum gets redshifted. If I measure these lines and compare them to the rest frame, I can figure out how fast things are rotating. Yes, question?
It's kind of similar to like this is going back a little bit, those black hole images where you saw the ring around and how the dust that was moving around, you could kind of tell kind of where it was coming towards you and going away, because those brighter patches, kind of like same kind of thing. Maybe not Doppler necessarily, but it was like because of the way they were spinning around it.
So with black holes, there's a few other effects coming into play. So you definitely have what we call Doppler beaming, where when you have a lot of motion, you can have an intensity increase. With black holes, though, the gravitational field is so strong that you're basically seeing the backside because everything gets curved, right?
Yeah.
So this is really literally like your ambulance that drives by and the frequency changes. So things that move towards you would be blue shifted. Things that are moving away from you are red shifted. And so you can do this for one line in one part of a galaxy. And so you could ask, for example, and this is what Hubble did. He said, like, if I look at one spectrum per galaxy, I can measure how fast that whole thing is moving away from me. You can also ask, what if I would do this measurement and I would repeat it over and over and over until I have all of these circles? I can compare the left to the right, to the top and the bottom, and I can look at the differential rotation between all of these parts. And so this is what we do with an instrument called SAMI, and SAMI is on the Anglo-Australian Telescope in Coonabarabran, which is about an 8-hour drive from here. This is that top end here. The top end's about a giant cylinder that's about 1.5 meters big. If you look closely, you can see someone is actually sitting in that top end at the moment. This used to be an old photographic unit, meaning back in the 70s, someone would sit up there and change photographic plates and actually take observations of galaxies. So they would spend all night pretty much in the top end of a telescope. We've converted this into an instrument where we're using a technique called hexabundles, where you take a bunch of glass fibers, same thing that your optical fibers run with. You remove the outer cladding, you glue it all together, and all of a sudden you have something that we call an integral field unit, meaning I can have the light that goes through here, go with a cable down into a spectrograph room. Spectrograph room produces these beautiful spectra. I can reconstruct it and I can make galaxy images. So this is a beautiful telescope. It's 4-meter diameter mirror. So it's about, the diameter mirror is about this part of the room. So it's big. It's clunky. It's about 70 meters high, this whole thing. Beautiful views. It's fairly green, which is a problem for astronomical sites. If it's green, it means there's a lot of rain. Rain is bad. That's why if you see observatories in the middle of the desert, you know you're doing a good job. This is in the middle of the rainforest. Not the best. You also have problems with local wildlife. And so one of my favorite stories is that one night we're observing, and you can see me sitting here in the top end. It's a while ago. But as I'm like, what you have to do is throughout the night, you have to replug these fibers and you have to put them in different positions on where you're measuring these galaxies. I should have put a trigger warning here, sorry. But I'm sitting in the top end and it's completely dark. Like it's completely dark. It's 4 a.m. in the morning. I'm just there with my head torch. And my colleague doesn't say anything. They just point towards something above me. And I'm sitting there, right? I'm having one of these hexagons in my hands. And this is the point where I have to realize every one of those hexagons is about $15,000 worth. And if I twist it or if I bend it, it will snap in two. And all I could think is, do not let go of this hexabundle, because I did not want to be that person that, ruined an entire astronomical survey just because there was a spider dangling above it. And so I just told my colleague, like, if it moves, let me know, because it was also like really clear. And it was beautiful observing. And I'm like, we just got to finish this and we'll deal with this later. So the next day, we looked at the spider was still there. It was. So I took, a CD case, DVD case, whatever it is. And I was just like, okay, I got it. And that's the point when I realized that a flat surface on a cylinder does not work. Giant gap on both sides. Luckily, the spider was fairly timid. But yeah, and then other nights we had them coming up behind the monitors when we were observing. And so, yeah, I always joke, at the AAT, you don't need coffee to keep you awake. The wildlife will do it for you. All fun aside, we spent 200 nights observing with this instrument. And by the end, we got all of these rotation curves, right? So these are 2D maps of galaxies. So every single one that you can see here is a galaxy, and they're all rotating. Some are really round, others are a little bit more edge on. But these are actual galaxies. And then the question is, I've told you rotation is that missing key, but how do you actually go from rotation into actual intrinsic ellipticity or intrinsic thickness? And so this is the only formula that I'll tell you. So we use a thing that we call the ratio of the ordered to random motion. So ordered is just your v rot. Sigma is your dispersion or the spread in your velocities. And so the diagram that we use often is this v over sigma, stuff that's really slowly rotating and mostly like those chaotic orbits, so those big ellipticals will sit here on the bottom left. If you take a very simple model, meaning an axisymmetric, so basically just a frisbee that you keep puffing up, you would follow the line from being the frisbee here on top, where here's the ellipticity defined as 0 is round, 1 is perfectly thin. Frisbees would sit up here, observed edge on, you go along this line. But then I already told you is that if I observe things edge on, it's really easy to figure out how thick it is. But once you start getting the inclination into place, it becomes hard. And so that's why you can't use that imaging. That's why you need this v over sigma. And when you do that, you can actually see that if I use inclination, I go follow these dashed lines. And so the dashed lines here is where the ellipticity changes. Sorry, inclination changes, but ellipticity stays the same. The dotted lines is where the inclination is the same, but your intrinsic ellipticity changes. So then you put in the real data, and so these are all of these SAMI galaxies, and we color-coded it by the galaxy's age. Here on the left is the raw data, here on the right is when we're using what we call a lowest locally smooth algorithm to bring out the underlying trends. And so the cool thing now is, if you look at where the young stuff lies, as compared where the old stuff lies, you see that they tend to follow these lines of this dashed line. And that was a line of constant intrinsic ellipticity. So all of the flat stuff here, all of the round stuff here. And so this is how we concluded that when you look at the intrinsic ellipticity, which is now shown here as a function of age, you find this really strong correlation. I say really strong. You might not be convinced that it's strong. You can use your statistical tests, but in astronomy, this is pretty good. In astronomy, we also fit a straight line for everything, and so that is your best fitting straight line. If you fit a slight curve model, you find a better solution. But this is the evidence where we found that if you look at galaxies, you find that their intrinsic shape is strongly correlated with age. Great. So what have we actually learned? Well, if you think back about that early Milky Way versus Andromeda collision, you have two galaxies that are sort of that intermediate age, but then in about 4 billion years or 5 billion years, they turn out to become that giant elliptical. And so what it's telling you here is that galaxies must evolve in a way that your disks grow puffier and puffier until they become really big and round. The slow puffiness can be by little mergers, so things like Magellanic Clouds, those are satellite galaxies colliding with our own Milky Way. You can think of internal processes where there is dynamical disturbances like those bars that you see that actually start to buckle and throw stars up and down as well. But what happens is that if you wait long enough, everything will just get a little bit rounder. And so coming back to sort of the work that I'm doing now, and so this is the last slide that I'll show you, the current project I'm working on is actually pre-selecting galaxies to be perfectly edge-on. And if you select them to be edge-on, you don't have to worry about inclination, you don't have to worry about all of those silly effects, and you can immediately compare stuff that, for example, in the center is really round, but then in the outskirts is really thin, versus stuff that looks, funky, versus stuff, and I don't know how well you can see it, some of these have like these giant X shapes, those are edge-on bars that we can observe. The goal, what we're trying to do here is we've selected galaxies that are basically the same stellar mass, so the same amount of stars as our own Milky Way, but they have different star formation rates, meaning some are forming stars at a really high rate, and so those are the really blue ones here on top. Others are what we call really quiescent, meaning they haven't formed stars in the last 10 billion years. The idea is that we're trying to find alternative pathways to how our own Milky Way was formed, and thereby learning something about how our own Milky Way formed. So in the same way that you can use, say, your brothers and sisters to figure out, hey, if I came from the same gene pool, what kind of variations could I find? Someone might have blonde hair, the other one might have dark hair, color of the eyes, but there will be similarities as well. And then you can also reverse it and you can ask the question, well, if I select someone that has blue eyes and blonde hair, like in this room, you would find two people that look very similar that way, and surprise, they come maybe from the same country a long time ago. So genetics, galaxies, very similar in that sense. We're trying to use the siblings or the analogues of our own Milky Way to learn something about how our own galaxy formed. So that's the work that I'm doing now. It's called the GECKO survey. It's using the Very Large Telescopes in Chile. It's a really cool program. If you want to learn more about this, I can talk for hours about it, but I won't do that now. I'll leave you with that last thought. Thank you. Questions? Sure, you were very quick.
What does GECKO stand for?
Bastard. I don't know it by heart. No, it stands for, I should know it. It's an acronym, but it's one of those really horribly contrived acronyms. It stands for generalizing edge-on galaxies and the chemistries, kinematics out to solar environments. Now, if there's a few extra letters there, yes, you're right. If there's a few missing letters there, you're right as well. It's one of those. Australian astronomers have this fun thing where they're trying to name all of the surveys after animals, in particular Australian animals. And so Caroline Foster here works on the magpie survey. I am also in a team that's called Wallaby Survey. There is Galar, which is one of my favorites, galactic archaeology. That's Sarah Martel that works on it. It's a bit of a tradition where you just try to find a cool name of an animal and then you acronym, meaning you come up with an acronym that fits that animal name. Yep. Yes, question.
You said at the beginning that that some of your research relates to whether or not our Milky Way is unique. My original question was actually going to be like, do we have any reason to think it's any different from any other galaxy? But after you said that little last thing there, I think my new question is, are we looking at other galaxies that are similar to the Milky Way to see if they all formed the same way and therefore we can conclude the Milky Way formed the same way?
I love that question. And it has so many layers. So first off, why would I conclude, for example, that the Milky Way might be unique? There's this mystery that we still haven't solved, that if you look at two different types of stars that have different chemical abundances, stars that are that have a certain type of chemistry that live in what we call the thick disk, which is that outer region, seem to be distinctly different from stars that live in the thin disk. And so the theory is that you need a special type of merger about 8 to 10 billion years ago in order to create that thick and thin disk, and with those very specific chemistries. That's one theory. But then people started doing more modeling and they said, well, actually, if I just take a random galaxy, but I let the stars move and change as a function of radius over time, I can actually explain that trend as well. And both these theories explain the data equally well. And so the issue then is you've got one galaxy, you've got two theories, you don't have enough data, right? And so from that sense, if you look, for example, at the simulations that do these predictions, they say only about 5% of galaxies would have that distinct feature of that thick and thin disk and with the special chemistry. And so then you'd argue, well, yes, our Milky Way is kind of unique because we need that special event. And so what we're trying to do here is we're trying to look in those upper regions of the galaxies and in those inner regions on the thick and thin disk to see if we can find that same chemical pattern in the stars. And so that will tell us, is the Milky Way one of a kind or is it unique? The other question you can do is, right, as you said, you can select things that on first sight look identical to the Milky Way, and then you can ask the questions, does every property line up? In a way, you're already self-answering your question, and because you've said, if I select things that look identical, maybe that's because every condition that they were formed in was the same. What is interesting, though, is that maybe there's also multiple formation pathways that lead to the final galaxy. And so that's one question we had, like, are we going to take that approach? We did it the other way around. We said, like, if we take things that have the same mass, but then arrange in those star formation properties, it means that they must have had a different star formation history and probably also assembly history. And so we're trying to use the variety that we're seeing to say something about how unique or how special the Milky Way is. But the jury is out. I would say the Milky Way is probably a very generic, a very typical galaxy. But how cool would it be if it is actually special? And so I don't know. It's one of those. That's why I love this research. Yeah.
So you were saying before, like, because we're dealing with a 2D projection, that's how we're kind of getting our data, like, trying to figure out the rotation and inclination is difficult. And on top of that, like, then when you're trying to also figure out distances, you got to do that luminosity, distance, candles and all that. What other things as a result of, like, trying to use astronomical data, what other difficulties do you have that aren't necessarily maybe like inclination and distance? Are there any other little things that really bug you that you wish could just be easier because it's, 3D?
I think there's a long list. The easy one though, and I will show you an image. I will deviate from my thing, and I will very quickly, because this is much better explained with a big, beautiful figure. And so we want color images, we want rotated ones. Which one is best for this?
So glad you just got these images.
Okay.
On your laptop.
So, I mean, I kind of have to.
Yeah.
So, I'm going to do, Hubble Space Telescope. Hubble Space Telescope is the best. This one will blow your mind. We really need to kill the lights now. Can you turn the lights off? I'm going to show you two images. I'll open that one, and I'll open. So, this is one of the galaxies in our sample. And so, the idea being is like, when you start to look in detail, and when you start to zoom in, everything looks terribly complex. And so one of the reasons why, this survey is really new, it's not just we're looking at edge-on galaxies, we're looking at a much higher resolution spatially than all of these other surveys have done before. And when you do that, and so this is not from our survey, this is from Hubble Space Telescope, but you can start to see all of these horrible dust plumes. And so pretty much when you're looking, you see all of the dark regions, all of the stuff there. When stars evolve through their life, they start to shed their outer layers and they produce a lot of dust. Dust are just particles that absorb the light that comes through. And so when you're looking at an edge-on galaxy, you're getting maximally extinction where that dust sits, right? And so this is one example. I'll show a really clear, you can clearly see that dust laying here, right?
Yeah.
And so this makes it both beautiful and extremely daunting because I don't know at some point whether this is what we call optically thin or optically thick. So I could be looking maybe 10% through that disk, maybe 50% or 100, but I'd never know. And so dust is just one of those things we'd love it for just to go away and never be a problem. We're observing in the optical. If you go into the infrared, the size of the wavelength becomes larger than your dust particles, and so that whole problem goes away. But you can't, we don't have integral field spectroscopy at those wavelengths yet because that is just too darn hard to develop.
Doesn't James Webb, isn't that one of the first that's kind of starting to do that?
So James Webb is perfect for this, right? From an imaging point of view. James Webb has beautiful spectroscopy, and so it can do that, but it doesn't have spectroscopy that fills pretty much every pixel on your screen. And so to give you an indication, the integral field spectrograph that we use, meaning I don't get one spectrum at a time, I get 300 by 300 spectra at the same time. So every observation that I do with VLT Muse, this instrument's called, gives me, at the very limit, very basic, 90,000 spectra in one single shot. And so on galaxies like this, we're getting 300,000 spectra that we have to analyze. James Webb does one spectrum, or maybe 10 or 20 spectra at the same time. And so in order to match sort of the spatial resolution that we're doing in the infrared, you would have to build an instrument like that, and that would be too costly. It's too expensive. Because it needs to be in space, because on Earth, the atmosphere also causes a lot of absorption. And so that's why James Webb is in space, because the atmosphere is really really opaque and glows at the same time. So yeah, great question. Other questions? Yes.
Does this? You said this that as stars go through their life cycle, they shed their outer shells.
Yes.
Does that decrease their mass?
A little bit, yes. And so, in particular, at the end of the life, a star like our own sun will go first through the red giant phase, and at some point, it goes through this asymptotic giant phase. Then it becomes a planetary nebula. if I say the number is going to be wrong, but think half of its mass will be blown out. A star like our own sun doesn't go supernova because it's not massive enough. But when a star does go supernova, all of its material pretty much, half of its material will just be blown out. Again, it's like huge factors. And so that all of that stuff is returned into the interstellar medium. And that's how we get what astronomers call everything heavier than helium metals, but it's how we get all of the heavier elements. Yeah. Other question? Yeah, James.
When you're saying that these galaxies are getting fatter,
Yes.
the mechanism for doing that, does it have to have interactions with other galaxies? Like if you just had a single galaxy, would it still get fatter?
Yes, but very slowly over time. And so this is where we call, like when we talk about what we call secular evolution, it's a very slow internal process. And so, for example, what you can have is you can actually have stars bounce off gas clouds that are really dense. And so this is scattering by molecular clouds that can puff up a galaxy slightly. A galaxy that has a really strong bar, I don't know if there's one in a beautiful example here. Yes. If you have bars, I don't know how well that shows up, but you sort of see that X shape in here.
Oh,
That's the signature. Like if I have a galaxy face on that has that giant bar in the center, if I observe that edge on, you start to see it as an X. And the reason for it is it's a dynamical instability, and at some point this dynamical instability starts to buckle. And so it really starts to throw stars up and down more. And that's why you start to see like that sort of a pattern going up, down, and up and down again. And so that's also a process that can do this. And so that's just an internal dynamical instability process. Both can do things. If I take what we think as the normal population and I would just like passively evolve all these galaxies, it still doesn't match sort of the big ellipticals that we see. And so we think it must be like an unknown ratio between the two, and every galaxy will have a unique mix. So our Milky Way, for example, we know it had a big merger about 8 to 10 billion years ago. Whether it's responsible for that unique chemistry, we don't know yet. But then about 4 billion years ago, there was a dwarf galaxy that collided with the Milky Way, what we call the Sagittarius dwarf. And that actually caused a lot of star formation. And our sun was part of that. So our sun was formed because there was a dwarf galaxy colliding with our Milky Way that caused a spur of star formation, and we're part of that. So it's pretty cool. Final question? If not, thank you for listening. If you've got any questions, I'm sitting on the first floor. I also teach second and third year astrophysics, where lots of this stuff will be done and treated as well. Thank you.
Thank you.
Get ready for the jump scare.